I don't know. It did that the first class too. Everything was set up, but until I went to that last click, it wouldn't come on. Okay. So chapter 8, we're still doing integration techniques we finished with now. Now we're doing improper integrals, and that's just going to be this section. A quick go through. Because somehow it seems like to me if it's an improper integral, not much you get. Evaluate an improper integral that has an infinite limit of integration. Okay? And we'll also evaluate an improper integral that has an infinite discontinuity. So there's two different things we're dealing with here. They look sort of similar. One is the horizontal asymptote, infinite limit of integration. The other, vertical asymptote, infinite discontinuity. And we'll see if we can evaluate either of those. So let's start with improper integrals with infinite limits of integration. Sounds like you can't do it. If it goes on forever, how can you do the limit? Well, the definition of a definite integral, the integral from a to b, f of x dx, requires that the interval a to b be finite. Furthermore, fundamental theorem of calculus requires that it be continuous on some finite interval, a to b. You'll study a procedure for evaluating intervals that do not satisfy these requirements, usually because either one or both of the limits of integration are infinite, or because f has a finite number of infinite discontinuities in the interval a to b. Either of these things, normally you say, well, you can't do it. Well, sometimes you can. Sometimes you can't, okay? Integrals that possess either property are improper integrals, okay? Note that a function f is said to have an infinite discontinuity at c when from either the right or from the left, the limit, as x approaches c from left or right of f of x is either infinite or minus infinity, okay? Either one of those. And you might say, how in the world could you integrate that? We'll see. To get an idea of how to evaluate an improper integral, consider this integral. The integral from 1 to b of dx over x squared. Okay? Now, we've eliminated the big problem. X can't be 0, so we're starting at 1. So we're just doing to the right. Okay? Well, we know this has an antiderivative of negative 1 over x, and we'll evaluate that from 1 to b. So we'll be negative 1 over b from the upper limit minus a minus, which is plus 1 over 1 plus 1. So it'll be 1 minus 1 over b. Okay? All seems fair. What if the b was going to infinity? Oh, you can't integrate something to infinity. You don't have a number to put there. But look here. If b was going to infinity, what's 1 over b? 0. So that limit would exist. I mean, that integral would exist, and it would be 1. Okay? Anything short of infinity, it would be something short of 1. You're subtracting and this is a positive number, obviously, from that. So it would be something, you know, b was 2,585,000 or something like that. That would be awfully close to 0, but it wouldn't quite. So that wouldn't quite be 1. But when you take it all the way to infinity, you'd have 1 precisely. So that's what we mean integrating something to, that was one form of the improper integral. The integral can be interpreted as the area shaded here from 1 to b of this function, 1 over x squared, and this would be something less than 1 because it's 1 minus 1 over b. But 1 over b is a pretty small, b is a, like 2.5. 1 over b would not be all that big. But they take it on out further and further and further, and it actually gets smaller, smaller, and smaller. So that integral can be interpreted as the area of the shaded region there. But b, as you get closer and closer to infinity, is going closer and closer to having a total limit, total value area under that curve of 1. Anywhere short of infinity, it's going to be a little bit less than 1. And what we do is, since you can't evaluate at infinity, obviously, what we do is take the limit as b approaches infinity and do an interval you can do. B is actually a number. You just don't know what it is. Do that, fill it in, then let b go to infinity, and in that case, you could do it. That improper interval can be interpreted as the area between the unbounded region between the graph of 1 over x squared and the x-axis to the right of 1. Can't do it back here, folks. Okay? It can't be from 0 there, because 0 is not even completely out of range there. It could have started at 0.5. Yeah, you could have done that one. Okay? It would just been a different value than at the end. But 1 is pretty simple. Works out nicely. Okay. So here's a definition of improper integrals with infinite integration limits. If f is continuous on an interval from a to infinity, then, now it has to be continuous. No breaks here. I'll get to the breaks later. Continuous on that interval, a to infinity, then the interval from a to infinity of f of x dx, if that is continuous, it would be the limit as b approaches infinity of the integral from a to b, f of x dx. Evaluate the integral first, then plug in and see if you can evaluate as b is approaching to infinity. If f is continuous on an interval from negative infinity to b, then you can't evaluate down here, but substitute and do a limit as a approaches negative infinity. Do the integral from a to b of f of x dx. Do the integral first. If you can do that, then let a approach negative infinity. If that has a finite answer, then that has a limit. I mean, the limit is met, and that is the value for the interval. Now, if f is continuous on an interval from minus infinity to positive infinity, do both of them. Okay? All right. You first do this one, and then with this one you go back and do that one. Then you do c to infinity, and then go back and do this one. And if all that works, then in the first two cases, the improper interval converges when the limit exists. Otherwise, the improper integral diverges. In the third case, the improper integral on the left diverges when either of these two diverge, okay? And that you have to go back and do both of these tests, the proper test on each one. If either one of them diverges, then the whole thing diverges. But if both of them converge, then that would converge. All right. I wasn't going to do the examples, but maybe we ought to. Let's see what happens with this one. Let's evaluate that. Whoa, let me get my pen set up. Here we go. There we go. All right. What would this be? Anyone know? Antiderivative of dx over x. 1 over x dx. That's the log function, log x. And we're going to evaluate that from 1 to b. What would that be? Log of, that's a pretty ugly log, isn't it? Okay. It would be what? Log of b. That is. So that would just be log of b. All right. Do you think you could let b approach infinity on this one? You could, but what would that give you? Log is a constantly increasing function. Constantly increasing. So it's not going to have a limit. That's going to diverge. Okay, so this one would not, and they said here, an improper integral that diverges, they have it introduced, let b go to infinity. As long as b is a finite number, that's your answer. But if b was going to infinity, no answer. Okay, so, but that is the answer here, log b. All right. They've written the problem wrong. They start doing the solution as if it went to infinity. But that wasn't the problem. They just said evaluate this. I thought they meant that, but I think they meant to have an infinity up there. And then you do the b, and then you try to plug it in, and it doesn't work. Because you see here, their solution, they start with the infinity up there. So I think the typesetter just messed it up, both in the book and on the slide set. This one doesn't have a limit, okay? The limit is b approaches infinity of log b is infinity. Does not have a limit. Okay. Now, so if you gather from those first two sort of examples, 1 over x, that doesn't have a limit. The area under here is b goes to infinity, does not have a limit. 1 over x squared did have a limit. They looked awfully similar, except of course the x squared comes down faster and then flattens out sooner, and that flattening out sooner, that's what does it for you. Now there's no reason that I can think of for that, except it just doesn't happen. 1 over x does not have a limit, 1 over x squared does. Now, they're skipping example 2. And both of those in example 2 converge, but since we're not going to test you on this, I'm going to let this one go. Let's get to, I thought we just did that. Yeah, oh, okay, this shows us that limit doesn't exist. All right, move on to I do want to do L'Hopital's rule, though, and they're skipping that one completely, too. So let's go back and do L'Hopital's rule. I think you had this before, right? You remember? Okay. It also worked with derivatives. It also works here. Evaluate this, the integral from 1 to infinity, this is how they should have written that one up there too, of 1 minus x e to the minus x dx. Okay. Well, this is not quite the one I thought it was going to be. I don't think you'll run into this much more. It's certainly doable, but since I'm not going to test you on it, let's just skip that and go on. I was thinking it was going to be something else. So let's go on and skip on through this and do improper integrals with infinite discontinuities. I just want to show you these things and then get to the rules that you can use. Okay, the second basic type of improper integral is one that has a discontinuity, infinite discontinuity at or between the limits of integration. In general, this will usually not work, okay? It usually will not work, but occasionally it might, okay? Because generally, say, if f is continuous on the interval from a to b, notice that b, though, is not included. A is included but not B. And it has an indefinite discontinuity at B. That's why it wasn't included, because it has no value there. It's going to infinity. Then the integral from A to B, even though it's not even defined at B of this, would be the limit of A to C as C approaches B from the left of f of x. So basically, you do the limit at a value where it does have that. It's continuous everywhere A to B. So anytime C is to the left of B, it's a continuous function, so you should be able to do an integral there. Okay? So do that integral, then let C approach B from the left-hand side, from the negative side, and see if that has a limit. If f is continuous on the interval from A to B, this time not including A, but including B, and has an indefinite discontinuity at A, do the same thing. Go from C to B, but C is now something close to A, but on the right-hand side of A. If this, because it's continuous, it should be able to integrate it, and then let the C approach A from the positive side and from the right-hand side, and see if that limit exists. If f is continuous on an interval A to B, except for some C in A to B, at which f has an indefinite discontinuity, then you split it at that C, and this one would be just like that one, and this one would be just like that one, and only these C's you were defined, these C's you're not defined, and it's all good. Lance, right? Cole. I mean Cole. I'm sorry. I knew that. Okay. Anyone else come in such a call right? Well, okay. Okay. In these two cases, the improper integral converges when the limit exists, okay? Otherwise, the improper integral diverges. In the third case, the improper integral on the left diverges when either of these diverges. It doesn't matter if one of them works, they both have to work. And if they both work, then it converges, okay? But if either one of them doesn't work or both of them don't work, then it diverges. Okay. Let's try this one. Where's our problem child here? Where? Yeah, but what about the radicals? Radicals in general are okay. Say again? Yeah, it's in the denominator, so the zero is our problem. So what we do then is evaluate this from, pick a letter, any letter, it doesn't matter, A to 1, and I don't like to do radicals if that's what you were talking about. Let's write this as x to the what? Negative 1/3 dx, okay? With that in mind then, that works. What would this be? Oh, I really should put this in the limit as A approaches 0 from the right-hand side, from the upper side. As A approaches 0. Second? Okay, x to the 2/3 preceded by 3/2, evaluated from A to 1, right? And that would be the limit as A approaches 0 from the positive side of, that would be 3/2 is the first part, minus 3 times the cube root of A squared over 2. 3/2 is fine. Okay? But how about the other part? What happens to that part as A approaches 0 from the left? Any problems? That goes to 0. So no problems at all. There's your answer, 3/2. Okay? If I can get on the right page here. Yes. And that's what they have. Okay? Now, let's just watch how they did it, which I think is very similar. Better be, anyway. The integral has a discontinuity at x equals 0. That's your problem. Okay? So we rewrite this as... they skipped a bunch of steps, didn't they? But they got to the same place. The limit is b approaches 0 from the left of that evaluated from 1 to b to 1. And that would be 3/2 times b minus 1 minus b to the 2/3 power. But as b approaches 0, that just goes to 1. So sure enough, that's 3/2. Okay. Now, this is sort of the key then, okay? Special type of improper integral, okay? If you have an integral from 1 to, this has an infinite limit, whatever you call it, the upper range here. If you have dx over x to the p, remember we did this when this was squared and it did have a limit, but we did it when it was 1 over x to the first power, it didn't have a limit. Okay? So here's the deal. It diverges anytime the p down here is 1 or less. If that p is 1.1, it's going to converge. And it will actually converge to this. 1 over p minus 1. Okay? So if that was 1.1, like I said, that would be 1 over 0.1, which would be 10, would be the limit of that. Remember when it was 2, when p was 2, that would be 1 over 2 minus 1 is 1. 1 over 1 is 1. And that's exactly what we got before. So this is the special case when the p is, when you have the limit and it's the upper limit is undefined, going to infinity, then if that's the case, if your p is greater than 1, anything greater than 1, then it's going to converge to exactly that. You don't even have to go through the limits anymore. You can just write down the answer. If not, though, if that p is 1 or less, it will never, ever converge. Okay? And that's your, that's the key there. Now, boy, jumping right over into a example 11 here. Solid formed by revolving about the x-axis, the unbounded region lying between the graph of f of x equal 1 over x, that's that thing, and the x-axis, so x is greater than or equal to 1. So here's where it starts. Doesn't go up here, but just starting right there. And they call this Gabriel's horn. It's an infinitely long horn, so it's a really heavy horn, so it takes Gabriel to hold it. Okay. Show that this solid has a finite volume and an infinite surface area. Okay. Interesting problem. And I don't know if it's really worth it to go on and do it, but it might be a good review of what we've been doing. What would be the volume of it? How would you do that? dx has come to mind. So you would split your thing into dx's, and this would represent a radius because you're revolving around the x-axis. So there's your y, and this, by the way, is the y. Okay, y is equal to 1 over x. So that would be the radius of your disk, right? Okay, and what would be the volume of that disk? Pi r squared dx. Pi r squared is the area, the thickness is dx. And you would integrate this from 1 to infinity, right? Well, the pi comes out, okay, and then your radius is your y, so this would be radius squared. Let's do this, would be the integral of 1 over x squared dx. Whoa! From 1 to infinity. Okay? Now, remember this? We just did that one earlier. That would be an integral of 1. Okay? So this would be pi. Has a finite volume, pi. That's it. The finite volume is pi. Okay? But the surface area, how did we do surface area? Remember how that went? Second? Okay. Well, what we did then, we didn't do we did our dx's still, okay? But then we had to translate that to be a little increment of arc length. Remember how arc length went? Say that again.
Do the derivative of a function, square it, add 1, and then take the square root.
All right. First take a derivative, and if r is this, it would be, there's your f, so f prime of x is equal to, let's write this as x to the minus 1. So f prime would be minus 1 over x squared. So far that's looking okay, isn't it? Except then you, like you said, add 1 to it, then take the square root of it. Okay? Let me just explain this to you. This acts like 1 over x, doesn't it? The square root of 1 over x squared is going to be, and let's see, when you squared it, you lost the minus sign. The derivative was minus 1 over x squared. Oh, but we had to square that, didn't we? Oh, I'm sorry, I forgot that. So that'd be 1 over x to the 4th, right? You squared it, then you add 1 to it, then you take the derivative of it. Well, that's looking a lot like a 1 over x squared, so that looks like it might work, okay? But it doesn't, because this thing right here, this p here, is the thing inside the parentheses here, well, we left off something. That gave you the arc length, but then you multiply the arc length times the that's the arc length here, but remember that arc length's going all the way around here. So then you do a 2 pi r. The arc length is just the r part, okay? And then you do a 2 pi r times that. So your integral is from 1 to infinity of 2 pi r, where r is this. So it's 2 pi 1 over x times the square root of 1 over x to the fourth plus 1. And so you see this actually comes up to be something like 1 over x squared. Square root of that, so that's like a 1 over x squared, but then you multiply it by 1 over x, that would be like 1 over x to, this is 2 halves, and that would be, anyway, this thing gets to be greater than 1. Because this is equal to 1, and you're adding something else to it, which makes it greater than 1. As soon as it gets, well, even just being 1, no way you can do it. Now, your dx was in there too. I don't want to go through all the details of it, but that's not going to work. So this is rather bizarre. The volume of this, which would be everything inside of it, is finite, pi. Okay? But the surface area, the stuff around it, is infinite and not even close to anything doable. So you're not responsible for this, but I just wanted to show you the rather unusual situation. Don't worry with the homework exercises there unless you just want to play with them. They're fun to do most of the time. So do whatever you want on those. And that finishes chapter 8. There's review exercises there. Now some of these you might find useful. And all these are at Calc Chat, the one I'm going to say. Any of the odds 1 through 7, 9 through 15, 17 through 25, 27, 29 to 33, 35, 37 to 43, 45 to 47, 49 to 55, 57 to 63, 65 or 67 or both, 69 through 73, 75, let's see, I think 75 is okay. I think 77 is okay. Don't worry about the rest of them though. Okay. All right, there's problem solving. If you want to look at that, you find it interesting, knock yourself out. Okay, now let's take a look at what we've got left. What we've done so far is the bulk of what Cal 2 is supposed to cover. But we also need to do a little bit in Chapter 9, a little bit in Chapter 10, and the first part of Chapter 11. I think that's going to take most of the rest of the month. I was thinking we might need to extend some, but in Chapter 9, we're only going to do 9.1 and 9.2, okay? I think this was said on the syllabus as well, and let me go back and look at this. We'll do 9.1 and 9.2, then we'll go to Chapter 10 and do 10.2, 3, and 4. So that gives us 5 sections there, and I think I'll give you a test after those 5 sections, and then we'll get going on Chapter 11 and try to finish 11, at least 1 through 5. 11.6 is where Cal 3 begins. Why they split it up, but the way Alabama does it, Cal 3 begins there. In every book I've ever taught from, that's right in the middle of a chapter. Okay, so that's where we'll begin that. So we'll do 9, 2 sections in 9, 3 sections in 10, have a test then, and then do 5 sections if we have time in 11, and that'll be our last test. Okay. So, they show this. So let me go on and show this. This, like we just said, there's the volume, pi r squared. R was your 1 over x, and that's something that we do definitely have a limit. You know, it converges to 1, so that's just pi. Okay, the second part, this is where it gets a little messier. remember it's 2 pi r times that arc length, which you gave correctly. Okay, I almost forgot to square that. And then times the dx. So that gives you that. The 2 pi out front, the 1 over x is your radius, okay? And then this is your arc length, just like we did, and then your dx. Well, let's see how they finesse it. That part is less than 1, okay? They say it's greater than 1. Yeah, of course it is, because you're adding something to the square root, to 1. 1 plus 1 over x to the 4th. However big this x is, it's still a little bit more than 1. So this is obviously greater than 1 on the interval from 1 to infinity. Okay? This one, already you know that won't work. That diverges. Okay? And so the combination of this, which is greater than 1, and this, which diverges, that it also has the divergence. So that's how they finessed it. Since this is greater than 1, you're multiplying it by something that already diverges. This is just going to diverge a little bit worse, okay? It doesn't really help. So they didn't mess around with that being like 1 over x squared. That doesn't really matter. The thing is, this thing diverges, and you multiply it by something greater than 1, it diverges. Okay, so the surface area is infinite. They don't mess around with anything else, just that. Okay. All right. And for some reason, my computer, it just shuts off for a moment. Okay. So let's move on to chapter 9. We'll just do 9.1 and 9.2. And these are pretty easy concepts, pretty straightforward. And what I might do is because you might need it somewhere, I might do just a quick slideshow of some of the other sections of the things that look like the most important parts of them, but we really need to get to chapter 11, so I don't want to spend too much with this. All right. So chapter 9 is infinite series, but we're going to start with sequences. Anyone know the difference in a sequence and a series? A sequence is just a collection of numbers, okay? Just a collection of numbers. We'll write the terms of a sequence. We'll determine whether a sequence converges or diverges. We'll write a formula for the nth term of a sequence, and we'll use properties of monotonic sequences and bounded sequences. Two different terms. Monotonic meaning moving only in one direction, in other words, not going back and forth plus or minus, either decreasing or increasing, monotonic sequences, and bounded sequences, sequences that do have an upper and or lower bound, usually both. So what is a sequence? A sequence is defined as a function, interesting, a function whose domain is a set of positive integers. So the domain is a set of positive integers, the range can be anything else. Although a sequence is a function, it is common to represent sequences by subscript notation rather than standard function notation. Because you see, a function, we usually think of being a continuous thing. Obviously, a sequence isn't, because its domain is the positive integers. 1, 2, 3, 4, those are the things. So you have nothing between 1 and 2. Though there's an infinite number of numbers between 1 and 2, it's not continuous. So quite often we'll use a subscript notation. So here's the sequence. In fact, this is a pretty simple one. 1 is A1, 2 is A2, 3 is A3. Certainly, the domain is the positive integers, okay, 1, 2, 3, 4, 5, 6, up and on. And the function is itself, okay? It's just y is equal to x, basically. Your sequence is 1, 2, 3, 4, 5, 6, and so on and so on. 1 is mapped onto A1, 2 is mapped onto A2, so on. The numbers A1, A2, A3. Now notice here, these subscripts here are your positive integers, okay? Okay, up to a sub n. Those are the terms of the sequence. The number a sub n is the ith term of the sequence, and the entire sequence is denoted by, and these braces is what they're called. Some people call them curly cues or whatever, but these are called braces with a sub n. That represents the sequence that's represented by that ith term designation a sub n. This would just be n, okay? In this case, that would be brace n. All right. So here's the terms of a sequence. Sequence a sub n will be the sequence of 3 plus minus 1 raised to the ith power. Okay? Now, why in the world do they give you the answers? Okay? What I want to do, let me get my pen back. Okay? A sub 1 would be 3 plus a minus 1 to the 1. The n, that's where your n goes. The positive integer, that's the first one. What would this be? Anybody? Say again? Is what? 2, okay. What would be a sub 2?
Oh, okay, you got to solve it. Okay, I'm sure.
Yeah. Yeah. Negative 1 to the first power is negative 1. 3 minus 1 is 6. Okay. What would the a sub 2 be? 3 plus negative 1 to the second, and that would be 4. A sub 3 would be second? 2. Okay. Anyone want to guess what the rest of these would be? 4, 2, 4, 2, 4, 2. Ad nauseum. Okay, that's what the sequence is. 4, 2, 4, 2, 4. Oh, I'm sorry. 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. I mean, just keeps on going. That is a legitimate sequence. Okay? Every one of those corresponds to a positive integer. 1, 2, 3, 4, 5, 6. Yeah, okay. On up. There's the terms of the sequence. Okay? Anyone want to guess whether that one converges? It's either 2 or 4, but doesn't narrow down to anything else. It just keeps bouncing back between 2 and 4. So this one, by the way, even though we haven't even talked about it, it obviously doesn't converge. Okay? That would be 2, 4, 2, 4, 2, 4, 2, 4. Okay. I'm not going to do the ones that show you the answers. Let's us do it. The B one here is the sequence B sub n is the sequence n over 1 minus 2n. Okay? So you give me the terms of that sequence. B sub 1 would be 1 over, okay, which would be negative 1. B sub 2 would be 2 over 1 minus 4, which would be, second, negative 2/3, right? B sub 3 would be 3 over, second, 1 minus 6. Okay, I couldn't hear what you were saying, which would be negative 3/5. Okay, Let's do one more, I guess. B sub 4 would be
4.
negative 4/7, right? Anyone want to make a guess? Is that one going to converge? Sure looks like it might. I mean, certainly the numbers are getting, the absolute values are getting smaller. Numbers are actually getting larger because these are negative numbers. Negative 1 here, negative 2/3 there, negative 3/5 there, negative 4/7 here. They seem to be converging. You know they're never going to reach 0, okay? So it's going to be going towards 0. So certainly 0 is a possibility, and I think that's probably a pretty real possibility. But no, maybe not, okay? We'll get to that later. But anyway, that's your sequence. That's all they're interested in now. Negative 1, negative 2/3, negative 3/5, negative 4/7. Okay? Okay, I'm going to erase this because I took up too much room. And let's do the C one now. C sub n is defined to be the sequence n squared over 2 to the n minus 1. Okay? What would C1 be?
1 over 2 minus 1.
Say again?
1 over 2 minus 1.
Which would be 1. Okay? C sub 2, goodness gracious. Okay. C sub 2 would be,
4.
say again?
4.
4 over
4 minus 1.
4 minus 1. I don't need a brace there. Yuck! I don't need my eraser to show up when called on. Okay. And this will be 4/3. Okay. C3 would be 9 over, which is 7, right? C4, 16 over, second, yeah, that would be 15. Okay. C5. Over what? 31? 31. All right. You're raising 2 to the nth power. Yeah. 2, 4, 8, 16, 32, 64. For a while there, it didn't look too good, did it? Because these were getting bigger. But don't stop too soon, because now now it's not as much bigger, and actually it was still greater than 1, but then suddenly now it's less than 1. And as you go on, it's going to get smaller and smaller. This one wins. Exponents always beat powers. Always. Okay? Exponential functions beat polynomial functions. So after a while, even though that could have been a pretty big number there, after a while this is going to win. And so it's going to, if you get large enough, that's going to continue getting smaller. There may be a limit, maybe 0 or some other limit, but it is going to be there. But they didn't ask that. They just said, what are they? They stopped at 16/15. Okay. Let's do D. Any questions so far? Okay. D. All right. Now, D sub n is going to be defined this way. This is called a recursive sequence, a sequence that's recursively defined. They tell you what D1 is, okay? And then they just tell you that D of n plus 1 is equal to D sub n minus 5. And that's all they tell you. So they already told you what D sub 1 is, so I'll write that down again if I can get my pen to ever show up. It seems to have lost its mind here. Okay? It's completely lost everything here. Okay. It decided to come back. Thank you. Okay. They've already told you what D sub 1 is. It's 25. Can you tell me what D sub 2 is? It's what? It's D sub 1, which is 25, minus 5, which is 20. Anyone want to guess what D sub 3 is? 15. D sub 4, 10. D sub 5, D sub 6, D sub 7, negative 5, and it gets worse from there. Okay? Anyone think this might convert somewhere? No way. Because the numbers are just getting, by same step, getting smaller and smaller and smaller, negative numbers. Even though your index, your domain is positive integers, it doesn't mean your range has to be positive integer. The first one we saw wasn't that. And this one is not that either. So for a while it looked okay, like it might be going to 0, but it scooted right past 0 and keeps going negative. We're not there yet, but just to let you know, they only listed 25, 20, 15, 10, and so on. All right. Now we're getting, okay. Now let's look at theirs. I didn't want to do, because they just tell you what they are. The terms of the sequence for the B, I probably should have gone back and done this as we did it, is a minus 1, oh, okay, I couldn't see that. 2 over minus 3, so minus 2/3, minus 3/5, minus 4/7, just like we did. Nothing new there. The deal is they're negative numbers, but getting less negative all the time, meaning they're getting closer to 0, further from minus 1, but there's always going to be negative, so you figure that has to have a limit somewhere. If nothing else, 0. Okay, this one, just like y'all did, and we just did the first few, 1, 4/3, 9/7, 16/15. We did a few more and saw they actually get less than 1 and just keep going downhill from there. And the terms of the recursively defined sequence, D1 is 25, and then you just subtract 5 from each one, subsequent one, so 25, 20, 15, 10, 5, 0, but it doesn't stop there. It just keeps going negative 5, negative 10, negative 15. So anyway, so now let's consider the limits of a sequence. We've already talked about it a little bit, but let's just hit it for what it's worth. All right. Primary focus of this chapter concerns with sequences whose terms approach limiting values. Now, I think what they mean is this section, not this chapter. The chapter is more about series. That's the name of the chapter. But you got to understand sequences before you can do series. Okay? Sequences are just a listing of numbers. Okay? It is a function. It's a function of the domain being positive integers. So everything depends on those positive integers, but it's not going to be a continuous thing. But even though it's not continuous, it still can converge if they seem to be going to some common value. Okay? And here's the sequence 1 over 2 to the n, which you could have had 1/2 to the n. That's the same thing because 1 to the n is always 1. But the first one would be 1/2, and then 1/4, and then 1/8, 1/16, 1/32, 1/64, 1/120. Yeah, it keeps on and on and on. Look like that might have a limiting value. Yeah, they're getting smaller and smaller and smaller, but always positive. So figure it converges to 0. Okay? Well, here is your definition of the limit of a sequence. Let L be a real number, then the limit of a sequence, the sequence A sub n, is L written this way. The limit as n approaches infinity of A sub n is L. If for every epsilon, boy, all these limits, I love these epsilons all day. For every epsilon greater than 0, there exists some capital M also greater than 0, such that the absolute value of A sub n minus L, that's the difference between basically the function value and the limit, just like we had before. That limit is going to be less than epsilon whenever you let your n, which is your domain, remember these are the positive integers, gets greater than that capital M. If the limit of a sequence exists, then the sequence converges to L. If the limit of a sequence does not exist, then the sequence diverges. And don't mess with it anymore. Just diverges, you can't do much with it. Okay? So it's a lot like all of our limits are going to be. Your epsilon, you pick an epsilon, any epsilon, just make sure it's positive, okay? Any epsilon greater than 0, however small you want it, okay? Then if there is out there some capital M also greater than 0, such that for your difference between the function value and the limit, A sub n minus L, absolute value of that is less than epsilon. You can make it less than epsilon anytime you let n be greater than that capital M. Okay? If you can't do that, then it diverges, doesn't exist. Limit doesn't exist. All right. Graphically, this definition says that eventually, for some n greater than that capital M, and the epsilon, however small you chose it, the terms of the sequence converge to L will lie within a band that's L plus epsilon and L minus epsilon is shown here. So yeah, out here for the 1, 2, 3, several of these, they're outside that band. But if somewhere out there you get past the point, say right here, there's your M, every one past that is going to be less than epsilon, then it converges to that limit L. Okay. If you had some that flew out somewhere here, nope, pick a larger. Keep going, but if you can never do that, then it diverges. Even though it may stay within a fairly narrow band, if you can't pick it for any epsilon, if you can't get it to narrow down in time, then it's not going to converge, it will diverge. Okay, if the sequence A sub n agrees with the function f at every positive integer, and if f of x approaches the limit L as x approaches infinity, then the sequence must converge to the same limit L. So in other words, if you can remember, positive integer was our n here, okay? And the a was the value, at that n. If a sequence agrees with some function f at every positive integer, that you choose, and if f of x approaches the limit as x approaches infinity, this can be a continuous function, but it has to agree at those positive integers to every one of them. And if that's the case, then you're fine. This function could have been doing this. the continuous function, but at the integral values, these are those, then if that function converges there, then so will the limit. The sequence converges to the same limit. Okay. So here's theorem 9.1. I'll make sure. Yeah. Let L be any real number. Let F be a function of a real variable such that as x goes to infinity, the function of f of x is going to some limit L as x goes to infinity. If a sub n is a sequence such that f of n for those integral values, this is a continuous value x, but if for every integral value, the same f defines what your a is going to be for every positive integer n, then the limit as n approaches infinity of a sub n is also that same value L. This f of x, this x can be positive, negative, anything, just continuous value. But if for those positive n's, these f sub n, f evaluated at the integral value, gives you those values for a, then if it converges as it goes. Notice they didn't say anything about negative infinity. That would make sense. So let's do example 2. Find the limit of the sequence whose nth term is this thing. Okay. Now this may require a little bit of digging back into the past. See if you can remember anything. What does that look like? Anyone remember what that is? It's what? That, yeah, e to the x will do it for you. If f of x equal e to the x, for all the integral values you'd put in here, that would be exactly what they, that would be the same. So f of n would be a to the n, which would be 1 plus 1 over n raised to the nth power. Have any of you ever done the continuous compounding interest? That's exactly what it winds up being. Okay, that is an n there. It's a pretty ugly n. See if I can make it look a little better. Okay. All right. Is that how they approached it? Yeah. Well, actually, it's just e, not e to the x. I thought it was e to the x. Back in chapter 5, 5.6, example 5, says you learn that the limit as x approaches infinity of 1 plus 1 over x to the x, okay, is equal to the number e. Okay. All right. So therefore, this sequence converges to the number e. Anyone remember approximately what the number e is? It's somewhere in the neighborhood of 2.71 blah 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 blah. You know, something around that number. Okay, that's what this thing converges to. Okay. So this wasn't quite true. F of x I think it would just be e, not e to the x. E. Because the limit as x approaches 0 is e. All right. Now, let's watch them do it. They may say it a little bit differently and perhaps better. You learn that blah, okay, this is what I was just talking about, that is the number E. So you can apply theorem 9.1 to conclude that the limit as n approaches infinity of a sub n is this thing. Okay, that's what they told us. But that, if this approaches E, this has to approach E. So they approach the same limit, and that limit would be the number E. Now, there are different ways in which a sequence can fail to have a limit. Almost sounds like our indefinite integrals from before, or infinite integrals from before. One way is that the terms of a sequence increase without bound or decrease without bound. They're not going to get narrow into a band. They just keep going up or they keep going down. There's no band you can get to that they're going to always stay between. That's one pretty obvious. These cases are written symbolically as shown. The terms increase without bound. They say the limit as n approaches infinity of a to n is infinity, which to me is a ridiculous statement because if it's infinity, there is no limit. So, I mean, that just seems crazy. And decrease without bound, and the limit is. Now remember, n is always going to positive numbers, okay, because it's positive integers, right? A sub n, the value of a sub n is going infinitely negative, okay? So that's one way. Increase without bound or decrease without bound. That's not two ways, that's one way. Either increasing or decreasing without bound. They don't mention the other way, okay, we'll get to that later. Properties of limits of sequences. Let the limit is n approaches infinity of a sub n be some L. And the limit is n approaches infinity of b sub n be some other number k. They both have limits, finite limits. Scalar multiple, okay, well they didn't say for c is any real number, okay. The limit as n approaches infinity of ca sub n is just going to be c times whatever the limit of a sub n. You can pull the c, that constant c, outside the limit, and then that will be L c times L. C is any real number. Sum or the difference. These sound so familiar, don't they? The limit as n approaches infinity of a sub n plus or minus b sub n is going to be L plus or minus k. Whatever. However you think that. The product. The limit as n approaches infinity of a sub n times b sub n is going to be L times k. That makes sense. The quotient, the limit is that n approaches infinity of a sub n over b sub n is L over k, as long as the b sub n is not 0 and k is not 0. So the b sub n can't be 0 or else that makes no sense. K can't be 0, that makes no sense. So that's the quotient rule. Always have to disallow 0 in the denominator, no matter what the situation is. All right. Now, any of you run into factorials before? You know what factorials are. Everybody, anyone who's not familiar with factorial, don't be shy. Everybody knows what factorial is. Good. Okay. Quite often that's stuff from finite math, and sometimes people get in calculus and never run into it. Okay, the symbol n factorial is used to simplify some of those formulas. They say of these formulas, which formulas are they talking about here? We've skipped example 3 and 4. That's why, where is the precedent, antecedent, or whatever for these? So let's go back and find some place where we can write this down. Okay, right here. Let's do example 3. Well, I can't get my pen to write. There we go. Now, example 3, you can go to larsoncalculus.com for an interactive version of this type of example. Okay? Here is your sequence. A sub n is equal to the sequence 3 plus negative 1 to the nth power. Okay? We've seen that before, haven't we? What were its terms? It started with 2, 4, 2, 4, 2, 4, dot, dot, dot. Right? Okay. Now, what about the limit? What you think? Does not exist. Now, that's not a problem that it's going infinitely large or infinitely small. That's not the issue here. What the issue here is, it doesn't ever converge. It just bounces between 2 and 4 and 2 and 4 and 2 and 4. So no matter how big an m you choose, you're never going to be able to get arbitrarily small thing. Your epsilon, any epsilon less than 1, not going to work. You can't say plus or minus epsilon from anything, because these are always 2 or 4 and 2 or 4 from now and forever. Okay? That limit does not exist. Not because it's infinite, it just doesn't exist. The sequence diverges. Okay? Okay. Now, let's go look at the B one. Let's try to see if we can get B in here. Did we do this one before? I think we did, didn't we? Can't recall for certain. Let's do it. Okay. Now, for something like this, the first one, you just almost have to put them down and see, oh no, it doesn't converge. This one, you could do the same thing. You could start with n equal 1 and n equal 2 and n equal 3, see what's happening. But you know, the other thing you could do is rewrite this as, well, no, that's not quite right. Little trick, I don't know if you remember when we were dealing, you see you're letting n go to infinity, so let's divide everything top and bottom by n. That's legal in most states, right? Anytime n is getting to be very, very big, it's going to be hard to do. So what does this become? N over n is 1 over n, that just is that, minus 2. Right? And as n gets very, very large, going to infinity, what does this become? As n gets very large, 1 over n is getting closer to 0. And so you wind up with negative 1/2. Now let's see if just looking at terms would have told us this, okay? So I'm going to erase this, and let's actually do some of those, okay? The first would have been, I'm sorry, I don't need the brace there anymore. Okay, 1 over a negative 1, right? And then you had 2 over negative 3, wasn't it? And let's see if I can remember the next one. Minus 3 over five. Remember? We did this one, remember? Minus 4 over 7. Minus 5 over 9, and so on, minus 6 over 11, minus 7 over 13. Okay. Right now, I don't know about you, but I don't see. So minus 1. Okay. Remember what we said before, it's getting smaller, getting closer to 0. It's negative and getting smaller, so certainly it has a limit of 0. Well, it isn't going to ever reach 0, but that doesn't mean it's its limit, okay? But if you finally start looking at this, you'll see this is basically 1 less than twice that. Oh yeah, 1 less than twice that, 1 less than twice. This is 1 less than twice this. This is 1 less than twice this. 1 less than twice. That's how we got it, So this is indeed getting closer and closer to negative 1/2. Never reaching it, but getting closer. So its limit is that. This tells us a lot faster than doing all those numbers. Okay, a whole lot faster. Okay. So that was example 3. Let's go to example 4. This is going to be a blast from the past. Show that the sequence whose nth term is a sub n. Now this time they're not putting it in the braces, they're just saying this is the nth term. N squared over, I've lost it, there it is, 2 to the n minus 1. We've seen this one before, haven't we? Okay? Show that the sequence whose nth term is that converges. Okay. Now, when we were doing these, at first they were getting larger, but then after a while they did start getting smaller. So we concluded they must be going to converge somewhere because they were always positive, but they were getting smaller. Very, very slowly, but they were getting smaller. So we knew they must converge, but, and that's all they say, prove that it does converge. Okay? Well, this is one of those cases that it might be better to go to the function form. F sub x would then be what? X squared over 2 to the x minus 1. Okay? All right, to the x minus 1. Now, what we're interested in, does this thing converge? Okay, so the limit as x approaches infinity of x squared over 2 to the x, did it again, minus 1, does that converge? Now, do you remember what we used to use a long time ago to deal with limits that either were 0 over 0 or infinity over infinity or sometimes infinity minus infinity, those weird kind of ratios? There was a simple test that was used for those. Anyone remember what it was? Fairly simple test. Has nothing to do with a hospital, by the way. Say again? L'Hopital's rule, okay. Now, interesting character, L'Hopital, and I don't really want to fault him too badly. To tell the story makes it seem like he was a jerk, but I don't think he really was. He was, I think, a very good mathematician, but one of his strengths, I think, was explaining math some fairly complicated areas of math. And he, I think, traveled around and studied under a variety of people, really, really top-notch mathematicians. And he then compiled the knowledge he was getting into a text. And I think it may have been one of the most comprehensive texts on calculus that had been written by that time. And he did it because he studied under some real giants, okay? One of whom was one of the Bernoullis. Remember, the Bernoullis was a family of really brilliant mathematicians and physicists, and must have been pretty good teachers too. Their sons were really great mathematicians and physicists as well. And he studied under one of the Bernoulli brothers and learned this from him and cited him in his text, his mathematics text. But no one had seen this before because Bernoulli had never published it. But because it showed up in L'Hopital's text, it became known as L'Hopital's rule. And Bernoulli, who was really a fairly volatile-tempered person, I think blew up when the people started referring to it as L'Hopital's rule. And no matter what L'Hopital tried to do, they never called it Bernoulli's rule. They always called it L'Hopital's theorem or rule. So remember how it worked? Yeah, it's the same as the limit as x approaches infinity of, derivative of the top is 2x. The limit of the denominator is, oh boy, do we remember that one? It's just like an exponential, because it is an exponential. It's 2 to the x, but then it's over log 2. That's my memory of it. I'm going to go back and check and make sure I'm not leading you astray. Far be it from me to want to ever lead you astray. Okay. Here we go. Derivative of, please tell me it's in here somewhere. Yeah, there it is. Number 6 at the front of your book. Derivative of u to the n No, that's not it. A to the, number 12. Derivative of a to the u is log. It's not divided by, it's multiplied. Sorry about that. It's log 2 times a to the 2. I mean, log 2 times 2 to the x. So it's not divided by, it's multiplied by. For some reason, I was thinking it was divided by. Okay. Better be what the book got to. Yeah. Okay. Now, the limit of that as x approaches infinity is, guess what? Infinity over infinity. That didn't help much, did it? Except, because it's still infinity over infinity, you can use L'Hopital's rule again. Bernoulli's rolling over in his grave. Okay. X approaches infinity. And what's the numerator here? 2 over log 2 is just a number. So that's just a coefficient. Times derivative of 2 to the x is 2 to the x times another log 2, so it's log 2 squared. Okay? It's not log of 2 squared, it's log 2 quantity squared. What's the limit of that as x goes to infinity? Which is 0. Yes. So that one, and if you remember back when we were talking about it, we said it's getting smaller, it's always going to be positive, so we know it has at least a limit of 0, but we didn't know if there's some number before 0. There's not. It's going to 0. Okay. And since the function does, that means the sequence does too. So the limit as n approaches infinity of a to the n, which is n squared over 2 to the n minus 1, and that minus 1 is immaterial here almost, that also converges to 0. Okay. All right. Now, that was example 4. It has absolutely nothing to lead us to this. It says to lead us to some of these formulas. In the book it says to simplify some of the formulas developed in this chapter. So it's not these formulas in particular. I see a little bit of motion here. It is about the time we usually take a break. Do you need one? Yeah, okay. Let's do one and we'll pick up here with this slide. Top of page 591. Okay, I'm going to pause this. All right. This is slide we had before I realized we skipped a couple of examples. Symbol n factorial used to simplify some of these formulas. The book says some of the formulas we'll be using in this section. Let n be a positive integer, then n factorial is defined as, and I usually count down, they count up. So if this was 7 factorial, it would be, the way I do it, 7 times 6 times 5 times 4 times 3 times 2 times 1. That's it. They do 1 times 2 times 3 times 4, up to 6, then 7. Okay. You're multiplying them. Each one is a factor. Each integer is a factor. As a special case, the 0 factorial is defined as 1. Bizarre but true. It doesn't follow any pattern. Certainly 1 factorial is also 1. Okay? 2 factorial is 2, and then from there on 3 factorial would be 6, 4 factorial would be 12, 5 factorial would be 60, you know, and on. From this definition, you can see that 1 factorial is 12, 0 factorial is 1, 1 factorial is 1, 2 factorial is 1 times 2 or 2, 3 factorial is 1 times 2 times 3, which is 6, and so on. Now, I don't know, I guess I always learned it counting backwards. You know, whatever the factorial was, just start counting down until you get to 1. And you don't even need 1 because anytime thing times 1 is what it was. Okay. Now, factorials follow the same conventions in order of operations as exponents. So treat them like the exponent. That is to say, just as 2x cubed and 2x in parentheses cubed are completely different things. This one you cube the x, then you double it. Here you double the x and then you cube it because it's in parentheses. Apply a different order of operations. So 2n factorial would be 2 times n factorial. So 2 times 7 factorial would be 2 times 7 times 6 times 5 times 4 times 3 times 2. Whereas 2n factorial would be 2 times 7, 14 factorial would be 14 times 13 times 3, on like that. They imply the order chop. Here what we have. This would be 2 times 1 to, as a factor, n times 1 times 2 times 3 times up to n. And this one would be 2n factorial would be up to 2n. So it would be n. Oh yeah, okay. I didn't see the extra dots there. Okay. Up to n times n plus 1 times n plus 2, all the way up to 2 times n minus 1 times, okay, times 2 times n. Okay. So this would be a far bigger number than that, is another way of looking at it. Okay. Another useful limit theorem can be rewritten, as for sequences, is the squeeze theorem. Okay? And how that goes. something that to read it makes perfect sense and just perfectly logical, but then to see it and how to apply it, sometimes it's easy to miss. The limit as n approaches infinity of a sub n is L, and that happens also to be the limit of b sub n as n approaches infinity. If there exists some integer n, now this is where it differs a little bit, some integer capital N such that for any a sub n less than or equal to c sub n less than or equal to b sub n, okay, then there exists an integer n that for all n's greater than that n, then the limit of c sub n is less than L, is equal to L, I'm sorry, has the same limit. Well, this is saying no matter what they're doing to begin with, A could be all over the place, B could be all over the place, C could be all over the place at small n's, but if after a while the A's and B's, the A is always down here somewhere, B is always up here somewhere, and C is always somewhere in between or equal to them, then as long as there's some capital N that you can find, that this will always be that relationship from there on for all n greater than that n, then C is going to also, as n goes to infinity, it's also going to have the same limit. Because A is less than C, and C is less than B, A and B have the same limits, C's got to have that same limit. The squeeze theorem, and some books call it the sandwich theorem. I've heard some other name for it, and I can't remember what that one is now, but it's some similar type name. Okay. So here's example 5. Show that the sequence C sub n, which is defined to be -1 to the nth over n factorial, converges, and find its limit. Okay? Now, this is one of those that because -1 to the n, every other n that you have here is going to flip from being positive, negative, positive, negative, positive, negative. Because -1 to an even power is going to be a positive number, and -1 to an odd power is going to be a negative number. So this is going to be flopping back and forth. But the deal is, that's just the sign of the coefficient, you might say. The real controller here is the n factorial. Okay? Now, like I just said, you could say there is a sequence A sub n that could be equal to 1 over, just call it -1 over n factorial, right? And do a B sub n that would be 1 over n factorial. Okay? Okay. Now, it doesn't take too much imagination to see where this is heading. As it gets bigger and bigger, let's just take 10. 10 times negative, 10 times 9 times 8 times 7 times 6. Well, what's that going to be? Where's that heading? 0 from the lower side. That's going to be 0 from the upper side. So guess what? They're both going to 0, and this is always in between that because they're equal to this one for odd ends and that one for even ends, okay? So it's going to be bouncing back and forth, and if both of these are going to 0, then C also has to go to 0. This squeeze theorem, okay? Now that's 1. Let's see if they use the same one. Let me erase this. To apply the squeeze theorem, you must find 2 convergent sequences that can be related to C sub n. 2 possibilities are, okay, they use a different one. -1 over 2 to the n and 1 over 2 to the n, both of which converge to 0. Okay, I like -1 over n factorial and -1 over n and positive 1 over n factorial, but both of them work. And both of them converge to 0. Now, the deal is finding a capital N such that past that it works. Well, if you think what this is, the first one would be negative 1/2. Next one would be positive 1/4. Negative 1/8, positive 1/8, all like this. And this would be 1/2, 1/4, 1/8, 1, like this. So that one's going to be, for n equal 1, that's just going to be -1 plus 2 minus 6 plus, well, it doesn't take long before that's always within these terms are like 1/2, 1/2 times 1/2, 1/2 times 1/2 times 1/2. Okay, those are those terms. These being minuses and these being plus. This one is -1, which is outside that, positive 1/2, which is outside that one, minus 1/6, that's still outside that, positive 1, 2, 3, 4, 1 over 24. Suddenly you're less, okay, because that's the this is 1, 2, 3, 4 would be 1/16. Yeah, 1, 2, 3, 4. Here now you're less. So anything beyond 4 for any capital N greater or little n greater than 4. If the capital N is 4, this thing's always going to be within that. This is going to be smaller, and they keep getting smaller. This one is just smaller by a factor of 2. This one's smaller by a factor of the next integer. So there, it's going to be that. So certainly this one works too. Okay, I think it's far easier to see using plus or minus 1 over n factorial. But, so let me erase this and read on what they say. By comparing the terms n factorial with 2 to the n, you see this is greater, so in the denominator this will be a lesser number. Product of these two, this is greater, so that in the denominator it will be a smaller number. These, again, 6 is less than 8, so then by the time you get here, this has gotten up to 24, this has only gotten to 16. So from here on, this is greater than that. So therefore, 1 over this is going to be less than 1 over that. So any n, capital N, little n, greater than capital M, whatever they call it, of 4, this is going to be the lesser number. Okay? I mean, this is 1 over this is going to be the lesser number. These will be less. So anything beyond that, these are going to be far bigger numbers than that. So your 1 over that gets very, very much smaller. So n greater than 4. Okay. So 1 over 2 factorial, this will be, okay, here's 1 over, negative 1 over 2 factorial here, positive 1 over 2 factorial there. Your 1 over n factorial starts down here, jumps up here, outside, just outside, inside, and then stays inside for the rest of the time. So therefore, any n past 4, greater than 4, that's going to converge. Squeeze theorem. Okay. I'll apologize if any of you have noticed I'm scratching a lot. Over the 4th, we were up at the lake, and I got eaten up with chickers, so I'm just itchy all over. They last for many days, you know, but anyway, mostly on my legs. Okay, so got one right here. It's going away, but it's still a pain. So by the squeeze theorem, it follows that the limit as n approaches infinity of -1 over 1 over n factorial is going to 0, because this was going to 0, and the positive of that's going to 0, and after n equals 4, beyond n equals 4, this is less than either, you know, within that, so it's got to go to 0 too. Now, absolute value theorem. This is top of page 592. For the sequence a sub n, if the absolute value of a sub n is equal to 0, that means if you only use the positive numbers here, and that's going to 0, then by all means, if these are plus or minus, they're going to 0 as well. If the absolute value, which is going to be the upper limit of those, is going to 0, then these are going to 0 as well. Because the a sub n could be plus or minus, but if no matter plus or minus, if the absolute value is going to 0, then so does that. Okay? The converse is not always true. Okay? So I don't think it is. That just because this is going to 0, that doesn't mean the absolute value will. Okay? I don't believe that one will work both ways. Oh, and that's all they do. Oh, well, that's all they show there. Then they say pattern recognition for sequences. This is what we're probably going to be using more than just about anything else. Sometimes the terms of a sequence are generated by some rule that does not explicitly define the nth term. For instance, that recursive, remember when we did that one? It didn't define the nth term, it just told you how the nth term was related to the n-1 term. Okay? In such cases, you may be required to discover a pattern of the sequence and to describe the nth term. That may be tough, okay? Or it may not be as bad as you think. Once the nth term has been specified, you can investigate the convergence or divergence of that sequence. Easy words to say, aren't you? Okay? So, now, I'm a little concerned. I've had my computer on since before 8:30 this morning, and I still have a red light on one of the batteries. I have a feeling not turning it on over the 4th may have just run my battery down. It shouldn't have, but it seems like it did. So I've got to make sure I don't lose my cord or my connection there. Find the sequence a sub n whose first 5 terms are these: 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9. Okay? And then determine whether the sequence you have chosen converges or diverges. Okay? Now, anyone want to hazard a guess about what this sequence could be, the a sub n? Now, this is actually probably one of the easier ones you'll see. Because what are these numerators doing? Yes, 2 to the n. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, right? What's the denominator doing? These are the first n odd numbers, which would be 2n minus 1, 2 times 4 minus 1, 2 times 3 minus 1, 2 times 4 minus 1, 2 times 5 minus 1, right? So that's basically what you got. Your a sub n would be 2 to the n over 2n minus 1. Okay, that's 2 to the n, not 2n. Okay. Now, then determine whether this sequence converges or diverges. Let's take a look. This would be 2, 1 1/3, 1.6. This is 1.67, basically 1.6. This would be just greater than 2, a little bit greater than 2. That's almost 3, isn't it? Greater than 3. Doesn't look like much of a chance that's going to converge, does it? Because 2 to the n is getting bigger way faster than 2 to the n minus 1 is. So I would say, just gut feeling, diverges like crazy. Let's just do the next one. 64 over 11. That's almost a factor of an 11. Then 128 over 13. No way. It doesn't look like to me. And they went back and used L'Hopital's rule, which I didn't think about using, but we could have. The limit as x approaches infinity of 2 to the x over 2x minus 1. Since that's infinity over infinity, use L'Hopital's rule. The limit as x approaches infinity. What would L'Hopital's rule give you? Been a long time, but we remember it, don't we? Log of 2. Why is my log going? Log of 2 times 2 to the x divided by 2, isn't it? Derivative of 2x minus 1 is just 2. And as that goes to infinity, as x goes to infinity, this one takes off and goes, this one stays 2. That's going to 0, that's going to infinity. So it does not exist. Okay. I don't like to say equals infinity because there is no number infinity. There is no limit. So it diverges. Sequence diverges. Okay. Does that make sense? Okay. First, note that the numerators are successive powers of 2, and the denominators are successive positive odd integers. So that could be 2 to the n over 2n minus 1. Okay. 2 to the n, that n is an exponent, the one at the bottom is a multiplier. Okay. And consider the function of real value f of x would be 2 to the x over 2x minus 1. That is infinity over infinity. So then we can take L'Hopital's rule and take the root of this or that. This gives you that. Here they put it behind before they put it in front. I don't care. And that gives you 2. That's going to infinitely large. That stays at 2. So that's going infinitely large. Limit does not exist. Diverges. Sequence diverges. Okay. All right. Now, this next slide is jumping a page and skipping the top of page 593, which I think is important, and also the bottom of 593, which is example 7. So let's go back and find some space. I think this is it right here. And let's go for it. Without a specific rule for generating terms of a sequence or some knowledge of context in which the terms of a sequence are obtained, it is not possible to determine the convergence or divergence of the sequence merely from its first several terms. For instance, although the first three terms of the following four sequences are identical, the first two sequences converge to 0, third one to 1/9, and the fourth one diverges. So here's what they're meaning. A sub n is equal to 1/2, 1/4, 1/8, 1/16, dot, dot, dot. Okay? B sub n is 1/2. I say 1/2 and write 1/4. Something wrong with the old gray cells. Okay. Okay. 1/2, 1/4, 1/8. Only on the third term does it become 1/15. C sub n is equal to 1/2, 1/4, 1/8, 7/62. What is going on here? D sub n is 1/2, I should have known that, 1/4, 1/8, 0. All right. Now, it took to the fourth term here before you could determine these were powers of 2. They look like these were, but this one confirmed that it's powers of 2. So this would be 1/2 to the n. Okay, and keeps on trucking. Okay, this one, what in the world was happening here? Say again? Okay, that is involved, but not quite. And again, to see this is almost impossible, okay? But it happens to be 6/, I'm taking it right from the book. I don't see this at first. n plus 1 times n squared minus n minus 6. No, plus 6. Comma, dot, dot, dot. Yes?
Is there a way we can figure that out?
That's what I was going to say. Not immediately, okay? We might find some later, but let's see. Okay? I've got to convince myself this is true. For n equal 1, this would be 2, and this would be 1 minus 1 is 0 plus 6. 6/6 is 1, so it'd be 1/2. So that worked. For n equal 2, this would be 3 here, and this would be 4 minus 2 is 2 plus 6 is 8. And this would be, what did I say, 3. 8 times 3 is 24, so that would be 4. So that's right. And for n equal 3, that would be 4. 9 minus 3 is 6 plus 6 is 12. 4 times 12 is 24. No. I must have done that wrong. This is 3. So this is 4. N is equal to 3, so this is 4. And this is 9 minus 3 is 6, which is 24 times 4. 48, yeah, and 8, 6 over here, that's right. But then the next one is 4. That would be 5 times 16 minus 4 is 12, plus 6 is 18. 5 times 18, 90, and 6 to 5, yeah, that would be 15. So yeah, that's right. Now, to answer your question, is there some way to figure that out? Okay.
Is there like multiple ones you can come up with, or is that like unique to that one sequence?
Say that one more
Is there
time.
like multiple like ways you can get that sequence, or is it
Yeah.
unique to that one?
The answer is I'm sure there is some way, but we haven't hit upon it yet. And I'm not sure we're going to hit upon it, so let's just leave that hanging for now. I don't know. Okay, this one is going to be something just as weird to have those three happen to come out being the same three, but then the next one is really wacko there. Okay, and let's just see what that one is, because I'll take it right from the book. N squared minus 3n plus 3, sure I would have thought of that, over 9n squared minus 25n plus 18. Dot, dot, dot. Okay? Now, I don't even want to try to do that. I'll take their word for it. Let's just do it for one and see if it works. I don't even want to do this. This would be 1 over 9 minus 9 and 18 and 27 minus 25 is 2, 1/2. That works. I don't even want to mess with 2 because that gets way too hairy. But I'll take the word for it that it works. Okay? Now this one is a little, let's see. I thought I had this one pegged, but I don't.
There could probably be something in the numerator that eventually gets to 0.
What's that?
It's probably there's something in the numerator that gets to 0 when in the score.
Yeah. It would seem that way. It would have to be. So this would be a 2 minus 1, a 3 minus 2. Waste too much time. Let me just see. Yeah. Minus n times n plus 1 times n minus 4. Sure. Okay. All over 6 times n squared plus 3n minus 2. Okay. All right. When n is equal to 1, this will be 2. This will be a minus 3. So that would be a minus 6, but then multiply by negative and you get plus 6. That 6 will be 1, so I'm guessing this goes to 0 then. Not 0, 1. 1 plus 3 minus 2, 4 minus 2 would be 2. Yeah, 1/2. That would be 1/2, yeah, perfect. That goes to 2. And when it gets to 4, that goes to 0. So something had to go to 0 there. But then when it gets to 5, it goes negative. Okay. Now, sort of to answer your question, do you remember back when we were doing those rules? I'm trying to remember which calculus course it was in, whether it was the beginning of this one or earlier when we had those. Let me see if I can't remember what you call them. I can't find them right now. But there are some techniques, when we're doing sums of i's, you know, example 7. Let's see if we can figure that one out. We'll come back to that, I think. Okay. I think example 7 is not listed here either, so let's do example 7. Negative 2 over 1, 8 over 2, negative 26 over 6, 80 over 24, minus 242 over 120. Okay. Now, get used to seeing these. 1, 2, 6, 24, 120. Does that remind you of anything? One times 2 times 3 times 4 times 5. That's your factorial. Your denominator is in factorial. 1 factorial, 2 factorial, 3 factorial. Get used to that one, okay? So we know our denominator, this is dot, 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 is n factorial. Okay. Now, let's see what's happening in the numerator. Seems like we got a minus 1 to the nth power, because it's alternating signs every time. So that's a good clue here. Now, what else is happening here? Sometimes, and here's one thing to look at, see if there's a ratio between terms. And let's just deal with numerators here. It's a ratio of 4, but this isn't a ratio of 4. That's 3 and a quarter. And this again is a ratio of something a little bit less than 3. And that's the ratio of something a little bit less than 3. So 3 keeps. Okay. Then decide, okay, determine the nth term. Notice that the numerators are 1 less than, I knew it had to do with the power of 3, okay? It's 1 less than 3 to the n, okay? 3 to the first would be 3, no. 3, is that right? numerators, oh, forget about the signs. 3 to the 1 is 3. Yeah, because the sign we're taking care of here. 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is, yeah, should have seen that. 3 to the 4 is 81, 3 to the 5 is, yeah, that's it. So it's, the rest of this is 3 to the n minus 1. Okay. Now, it says determine now whether the it converges or diverges. Okay. Now, again, you have this powerful factorial in the denominator. In the numerator, you have just 3 to the n, basically. Okay? Can't get any greater than that. So for a while, this is going to be less than or equal to, and forget about the signs. Let's do the absolute value one. N, I'm sorry, 3 times 3, 3 times 3 times 3. Okay. The numerator is always going to be less than that. 3 times 3 times 3 times 3. Okay. Always going to be less than that because you're subtracting 1 from it. This is going to be 1, 2, 2 times 3, 2 times 3 times 4, 2 times 3 times 3 times 3, 3 times 3. That should be 5 of them. And this will be 2 times 3 times 4 times 5. Okay? All right. When you get to 6, 3 times 3 times 3 times 3, 3 times 3, and it's 2 times 3 times 4, 5 times 6. Oh, I left off one. That is times 6. This is times 7. Okay. From here on, this is less than 1. And it gets considerably less than 1 from here on. Okay, this is greater than 1, admit it, okay? But this overwhelms this in no time. So basically, past, we do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I think about this next one, you'll see that the denominator is going to exceed the numerator pretty majorly, okay? And from then on, so that will be converging. And what will it be converging to? 0, okay? So it does converge to 0, okay? All right. And like I said, if you can show that the absolute value converges, then it guarantees that the other one does. And I think we showed it. Okay. So they don't show it, so let's move on. All right. Goodness, I'm getting so hungry. All right. Monotonic sequences and bounded sequences. Okay, I think this may be near the last thing that we cover in this section. Here's our definition of monotonic sequence. A sequence A sub n is monotonic. Mono means one. Tonic means no. It's basically one direction. When its terms are non-decreasing, which means that they're either increasing or stay the same. So A sub 1 has to be less than or equal to A sub 2, less than or equal to A sub 3, less than or equal to A sub 4, all the way up. Always the terms are either the same or getting bigger, same or getting bigger. Monotonically, I usually say increasing, but the more proper thing is non-decreasing. or when its terms are always non-increasing, meaning that a sub 1 is always going to be greater than or equal to a sub 2 gradually as you go through this. So they may not be always decreasing, they could be the same, but they're never increasing. These are never decreasing. That's what a monotonic sequence is. Either one or the other. And I usually say monotonically increasing or monotonically decreasing, but the more proper word are monotonically non-decreasing or monotonically non-increasing, meaning these never get smaller, these never get bigger. Okay, so let's determine whether each of these sequences given having the nth term is monotonic. Is it monotonic? What you think of that first one? No, we've seen that one before. That's the one that goes 2, 4, 2, 4, 2, 4, 2, 4. It's neither increasing or it's always alternating. How about this one?
Yes.
Yeah, that looks like it would be because you can, well, we looked at it and you could divide everything by n, and then this would be 2 over 1, okay? But then the next question is it increasing or decreasing? By dividing by n, you're changing its direction, basically. So if it's now 2, before it was more like 1/2. So that would be, I think, decreasing or non-increasing. Okay? Believe that's right. We'll come back and check on that. How about that next one?
Yes.
Okay. Yes, you say. Okay. If my memory's right, this one starts off increasing, but then starts decreasing. So that's not monotonic. Because remember, for n equal 1, this will be 1 over 1, right? For n equal 2, that would be 4 over 3. Looks like it's increasing, right? N equal 3, that would be 9 over 7. Still look, ooh. No, 9 over 7 is less than 4 over 3. Oh, is it? Hard to say. Let's go to the next one. That would be 16 over 23, right? No. Goodness, where's my brain today? Over 15. Okay. 16 over 15. That's getting closer to 1 again. So it was increasing and now it's decreasing. So that's not monotonic.
So monotonic only means like if it has one direction, not necessarily the sign.
Say that one more time.
So
It means for every term, it either can't be increasing or it can't be decreasing, okay? And this one, I think we did good. So yeah, it's not the same. This one, I'm pretty sure that's going to be, and let's just take a look and see if I said it right. For n equal 1, that would be 2 over 2, which is 1. For n equal 2, that would be 4 over 3. So that's increasing. N equal, I said it backwards. It is increasing. It's not decreasing. N equal, that was 2. 3, that would be 6 over 4. Yeah. So that's non-decreasing. Okay. It is monotonic and it's going one direction, each term is bigger than the previous term. None of them are the same size. This one, though, they start out getting bigger, and then they start getting smaller. Okay, so that's a no. So let's see if I got it right. Okay. That sequence alternates between 2 and 4, so it's neither increasing nor decreasing. It's alternating. Okay. Is not monotonic. Okay. The next one is monotonic because each successive term is larger than its predecessor, so it's non-decreasing. Okay. To see this, compare the terms b sub n and b sub n plus 1, and you'll see it's always larger than the previous one. Okay. Note that because n is positive, you can multiply each side of the inequality by 1 plus n and 2 plus n without reversing the inequality sign. Okay. Fine. Okay. I really don't see what that last sentence, what significance that is. But this one, so let's multiply it by n plus 1. And so that's the nth term, and compare that to the n plus first term. And your numerator is increased, that be 2n plus 2. The denominator is just n plus 2. So whatever that is, the numerator is growing faster than the denominator. That would be the best way to do it, not dividing by n. So 2n plus 2 this time they multiplied this by n plus 2, but they did it 2n plus 2. Still don't see what they've done here. They multiplied this by n plus 2. Oh, I guess they multiplied by n plus 1 times n plus 2. I guess that's what they were saying. It's not what I understood them to say. Well, I guess that's what they meant. So they multiplied this by n plus 1 times n plus 2. You lost the n plus 1. You have this times that. Multiply this by n plus 1 times n plus 2. Oh, this denominator is n plus 2, so that wipes out that. So it's n plus 1 times this, okay? What they did was legal, but the question is now which of these is greater? Seems like a very awkward way to do it. It would be 4n plus 2n squared, and this would be 2n plus 2n squared plus 4. Yeah. Okay, so these two terms are the same, these two are the same, and this 0 is less than 2. So, clever to think of that. I don't know what brought that on, but that's what they did. Okay, so that's always the case. So always the left one is less than the right one. So starting with the final inequality, which is valid, you can reverse the steps to conclude the original inequality is also valid. Okay. This sequence is not monotonic because its second term is greater than both the first and the third term. So the second term is the max, is what it says. Started increasing and then started decreasing. So it's not monotonic. note that if you drop the first term, the remaining sequence is monotonic. So if you go far enough, it does become monotonic, but it's not always. Now, okay. So here's a definition of bounded sequence. A sequence A sub n is bounded above when there's some real number, capital M, such that A sub n is always less than or equal to M for all n. So there's no value. If you find the M and that all these A sub n's always are less than or equal to that, then it's bounded. The number M is called an upper bound of the sequence. 4 million may be the upper bound, but 350 may also be an upper bound, so don't pick it too large. The sequence A sub n is bounded below when there's some real number n such that for all n less than A sub n, less than or equal to A sub n, for all n. That number n is called a lower bound for the sequence. It may not be the only one, but it is a lower bound. Now the sequence A sub n is bounded when it's bounded both from above and from below, and then is bounded. And we've seen examples of that when they started off like this, but then narrowed down and did that. So this is upper bound, this is lower bound. Everything else is between those. Okay. Now, we've also seen some that do like that, not bounded at all. Lower bound maybe, but not upper bound. All right. One important property of the real numbers is they are complete. Okay. Informally, this means there's no holes or gaps in the real number line. A set of rational numbers does not have that completeness property, because any irrational number is going to be between two rational numbers, and therefore if you take those out, there's a hole there. Okay. So rational numbers are not complete, real numbers are complete. Imaginary numbers on the real number line, they're not on there. Okay, so they don't count. The completeness axiom for real numbers can be used to conclude that if a sequence has an upper bound, then it must have a least upper bound. And that's what I was talking about. Don't pick 4 million and 350 is going to work. But 350 may not be low enough. Find the least upper bound, and the least upper bound that is less than all the other upper bounds for that sequence. Okay? But it's probably going to be the maximum value of your sequence. Okay? Now, this is not an example, but it's shown in the book. For example, sort of like one. The least upper bound of this sequence, n over n plus 1. Okay? Well, that would be 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, 6 over 7. There it is, n over n plus 1. Okay? Is 1. It's not in the sequence, so it's not ever going to be 1, but that is the least upper bound, is 1. Because each one of these is getting closer and closer to 1. 715 over 716. 4,000,005, yeah, you got the idea. It's getting closer and closer to 1, but never reaches. So that leads to a bounded monotonic sequence. So if a sequence is not decreasing and has an upper bound, then it has to be convergent. If the sequence is bounded and is monotonic, either increasing or decreasing, bounded meaning it's bounded on both ends, okay, above and below, and it's monotonic, then it has to converge. There's just no way around it, because it's bounded. It's got to approach that bound or this bound over time. It does converge. All right, so here's example 9. I think we have time for it. Here's a sequence 1 over n. Okay. They say it's both bounded and monotonic. Is that true? Let's name some of the terms in that sequence. What's the first one? 1, 1/2, 1/3, 1/4. You got the idea, right? Okay. Now, number 1 is bounded. On the upper, 1. Nothing ever gets greater than 1. On the lower, 0. It never reaches 0, but it's bounded by 0. Okay? So therefore, it must converge. And of course, it must, because it's a monotonically decreasing function, non-increasing function, that means it must be bounded. The converging must be 0. Okay? Now, here's I hate it, they tell you the answer. Here's a sequence, n squared over n plus 1. That's your b sub n. Okay? It's certainly monotonic. The first entry is 1 over 2. The second one is 2 over 3. The third one, no, 4/3. Next one is 9/4, 16. Did I skip one? No, yeah, 16 fifths. Okay. It's certainly increasing. Okay. So it's monotonic. 1/2, 4/3, 9/16, bigger and bigger and bigger. It is bounded below. Doesn't get any lower than 1/2. So bounded below, but it's not bounded above. So it has to be bounded above and below to be bounded. And so this is definitely not converging, it's diverging. Big time. Okay? Now, I sort of hate doing these, they give you the answers. Okay? Now, how about this one? -1 to the n. What would be some of the terms in it? Well, okay, -1. Oh. It goes back and forth between plus and minus 1. It's bounded. Upper bound of 1, lower bound of -1. Definitely bounded. But it's not monotonic. Okay? Because it's going up and down and up and down and up and down. So it's not monotonic. Now, you can't say for certain that's going to be divergent, but we know it is. This one is. So it has to be both to know that it converges. All right. That was example 9, I think. Oh, and that finished 9.1. So homework exercises here would be any of the odds 5 through 9. They're all at Calc Chat. 9's at Calc View. 11's at Calc Chat. And I would try to do all 4 of 13 through 16, even the even ones, even though only the odd answers are at Calc Chat. But this is just matching the graphs. You should be able to do that. Okay. Do either 17 or 19 or both. They're both at Calc Chat. 21 or 23, they're both at Calc Chat, but 21's at Calc View. 25 or 27, they're both at Calc Chat. Any of the odds 29 to 41, they're all at Calc Chat. 29's at Calc View. Any of the odds 45 to 51, they're all at Calc Chat. 49's at Calc View. 53 to 59, they're all at Calc Chat. 53's at Calc View. 61 or 63, they're both at Calc Chat. And then do any of the odds 65 well, let's say 65 or 67, they're both at Calc Chat. If you want to explore doing 69 or 71, they're both should be at Calc Chat. 73s should be at Calc Chat. 75s are proof. If you're interested in doing that, it should be at Calc Chat. 77 and 79 are both true-false. You could probably find those both at Calc Chat. Any of the odds 81 through looks like 85, they should all be at Calc Chat. 87's are proof, and 89 are both proofs. They should be at Calc Chat if you're interested in doing those. Whew. Goodness gracious, I'm running out of steam. All right, that's about it for 9.2. Well, I mean 9.1. Any questions on 9.1? I think we're just about out of time, aren't we? So we'll have to call it quits there, even though I think I'm cheating you out of a minute or two of your tuition dollars, but get over it. And we'll end